And now in this lecture over here, allow me to give this talk. It could be a short lecture, but allow me to give a talk about how chain rule can be seen as, or can be understood as related rates right here. Okay, I do believe that there are not too many professors out there pointing this out right here, but allow me to mention this in this particular lecture right here. And so I intend that this lecture here is for any calculus students who are who is going into any academic goal, like their academic major or any career path. Anyone learning learning calculus on any particular career path can view this lesson here and benefit from it. Okay, and this lecture in particular is intended to be as a continuation. I mean, if anyone is viewing this, this is meant and intended to be a continuation after you have learned from my general understanding or from my lecture where I gave the general understanding about related rates. So most importantly, it's still about related rates, but I want to point out how chain rule can be seen and how can be understood as related rates. And so definitely it is required that you in order to arrive at this lesson right here, you must have watched or viewed my other lessons where I introduced or gave the general understanding about related rates, so that you can have a solid understanding of what related rates are all about, and then this is the right place for that. And then aside from that, preferably this lesson will be it will be beneficial to view this lesson after you have seen some of my other videos where I point out specific examples of how we apply the related rates. But that's just something preferably that it'd be better if you've seen those some of those applications. But otherwise, if you have not seen any of my video lecture about how I apply the related rates into working through problems like that, then that's completely okay. Okay, it's not as highly required, or it's not as anything that's strictly required. It's just a high recommendation. All right, but other than that, let's get into it. Let's get into seeing how chain rule can be seen or can be understood as related rates. Okay, so now I'm gonna erase the board space here. So as you have seen enough through my general lecture about to give the understanding a general understanding about related rates. So now let me bring up the following problem right here, and assuming at this point you have already seen and have a clear understanding of what related rates are all about. So I'm not going to beat around the bush anymore, and I'm moving on here in this lesson, assuming you already had some solid background enough through my earlier teaching about what related rates are. So now let's say we're in the following situation, we're in the following problem right here. So allow me to bring up a problem that promotes the idea, that demonstrates the idea right here. So we have an equation. So the whole idea about related rates, we have an equation where variables are involved all over. So here my equation is as following. How about y equals a 5x cubed minus square root of x. Okay, it's a simple equation. I mean, anyone arriving at this lesson should not be unfamiliar with an equation like this. It's just an equation with standard powers here and then square roots, maybe some fancy square roots involved, but there's nothing unusual about an equation like this. Okay, and then yes, as the goal for this problem, as the instructed as some instruction for this problem here, let's say we want to differentiate. Okay, we want to differentiate. And then also, I have spent a good amount of time in the general lecture about related rates to explain the concept about what it means by differentiate in terms of, so differentiate this equation in terms of, okay, in terms of t. And this is back to what I said earlier. I explained hopefully thoroughly enough in my general lecture where I gave the understanding about related rates. But the whole idea now is that t is a variable that's not currently present in our equation here. Our equation only involves x and y, just two variables. So in some other problem, it could be another equation of z and v, or s or w, but the point now is that we want to differentiate in terms of another variable that's not currently present in this particular equation. And that's the whole idea. And then so because of that, so now we, again, I am assuming that anyone already understood, already learned and understood well enough how to differentiate something like this in terms of t. So yes, the key idea is the implicit differentiation, and then behind the scene there's a chain rule that involved right here. And so now if I'm saying we differentiate in terms of t, then that means on each variable here I'm going to see y as a function, okay, y as a function of t, or in short. So this idea once again is brought in my lecture where I gave the general understanding of what related rates are all about. So I want to see, so when we're asked to differentiate an equation here in terms of t, some variable that's not currently present in this particular equation, then it's our responsibility to see any one of these variables, to see all of these currently present variables as they're all as functions of t. So y is seen as is understood as a function of t, or another way you can see that we can see y as a y of t. Okay, that's how I'm seeing it, or like that. So now, and the same with x. X has to also be seen or understood as a function, okay, of t as well, or in another way of saying, or x of t. But it's just we just sadly don't know an explicit. We just sadly don't know an explicit expression of y in terms of t and x in terms of t. We just don't know how these two functions are explicitly written in terms of t. We just don't know that information. But we have to keep in the back of our mind that the y is understood as a function of t implicitly, and that's where implicit differentiation again will be coming in handy right there. And then x as a function of t implicitly. All right, so in that way, once I've done beating around the bush enough and reminding some of the basic information, understanding, now let me move on to the other board right there. And so now with this particular equation, yes, y equals 5x cubed minus square root. So now at this point it would be beneficial to write the square root of x as x to the power 1/2. But now any one of these two variables, x is a function of t and y is also a function of t. And so to differentiate in terms of t, even though we don't know how each one of these variables is written as a function of t yet, because those are both completely implicit functions of t. But I'm still going to apply so you have learned this symbol formally from my lessons where I talked about implicit differentiations and related rates. And so we're going to apply our notation that's indicating we differentiate both sides in terms of t, where t is a variable that's not currently present in the equation. Okay, and so in that way, let's proceed. And so at this point, I believe no one viewing this lesson, provided that you have already learned from my general the lessons about the related rates as well as implicit differentiation, then you should not be unfamiliar with this. Anyone viewing this lesson should be familiar with this the particular symbol right here and the way how I operate. And so on the left hand side, that produced for me a dy dt, simply just that. And again, the whole idea, the key idea behind the scene here is that we're working with functions, with multiple functions that are implicit functions. Okay, multiple implicit functions that are functions of t. And so sadly, we don't know an actual function of how y is in terms of t. So the only thing we can do, we write it as a derivative dy dt implicitly. All right, so all of a sudden we realized again we're done with the left hand side and nothing better than just a dy dt here. The left hand side, yes, there are two terms connected by the subtraction here. So that means I can work separately with the 5x cubed and differentiate that in terms of t, and then subtract the derivative in terms of t of the x to the 1/2 term. But now again, recall from what I explained earlier on the other board, even the x variable here in our current equation is a function of t implicitly. Okay, so now upon realizing that x is also a function of t implicitly, then, okay, so in my next step, allow me to move into one more step. So the left-hand side stays the same, dy dt. The right-hand side here, keep in the back of your mind, x is a function of t. X is a function of t, and so that idea about implicit differentiation or the chain rule comes back here. See this as, I see this as the chain rule says, because of 5x cubed is the same as 5 times some function x of t implicitly, and then cube. So I brought it in because I'm about to use the chain rule. So chain rule says to take this derivative. The chain rule says to take this derivative in terms of t, okay, we need to, and this is just a quick little scratch work that I'm doing sadly right here in this space. So chain rule says there's an outer function and there's an inside function. So we're looking at the derivative of the outer function, of the outside function. So 15 times x of t, but now needless to write x of t, just 15x squared, that's the derivative of the outside function, and I have to multiply with the derivative of the inside function, which is nothing but just, sadly, a dx dt. And again, the reason we added up with that dx dt because x is implicitly defined as a function of t right here. We did not know what expression exactly that was for x as a function of t, so we just leave that as an implicit the function, and so consequently we had to end up with an implicit derivative for x. So the dx dt is just our best solution at that point, right there. All right, so now I'm going to take all that here, put that in there. So after all that explanation, then I'm going to, first term here is 15x squared but times the dx dt. All right, and again, even though I tried to get in some more, I tried to bring back some more details from related rates, but I am sure anyone viewing this lesson should be fluent enough with what I was doing up here, without seeing too much of my reminding details right there. All right, so now allow me to pick up pace on the next one. So the next one is under the very same argument, the very same logical reasoning. So I have a subtraction term. And so now x being understood as a function, x is a function of t. X is a function of t. But now x here is being raised to a 1/2 power, so the raised to the 1/2 power is an outside function. So taking the derivative of t here, chain rule says we're looking at 1/2 times x to the minus 1/2. Okay, nothing surprising about that because here we just have a power rule over here. And then chain rule says we must multiply with the derivative of the inside. So the inside of the 1/2 power here is that x of t as a function, as an implicit function. And now I can do nothing by just indicating there as a multiply with a dx dt. So again, I have to multiply with the implicit derivative of x as a function of t. All right. So I start mentioning about chain rule a lot because chain rule is so important. It's everywhere, but that's not how it's connected to the topic of our discussion, where I talked about seeing chain rule as related rates. We didn't get there yet, even though it's all about chain rule. We bring it all over. Okay, and so now. Yes, for anyone, after seeing my lessons on the general understanding about related rates, then you shouldn't be surprised how I got to this point right here. And so up to this point right here, it should be easy enough to understand for anyone who have already viewed my earlier lessons, my earlier lecture about finding related rates. These are related rates. We got dx dt as a rate, dy dt as another rate. They are rates in terms of t. They are instantaneous rate of changes of y variable changing in respect to t, and also instantaneous rate of change of x variable changing in respect to t. But now in the end, we call them related rates because these two rates, the dy dt as one rate and the dx dt as another rate, they both exist in our equation and they are related through this equation. So again, that's just a reminder of what related rates are all about. Okay, but that still did not get to the main point of what I was talking about. I want to show how chain rule can be understood, can be seen as related rates. Okay, so now from this equation right here that already showed related rates, allowed me to move on a couple further steps right here. Okay, so I hope you're all ready. So this is something new that I'm adding on right here. Everything up to this point is still just from experience you've had from my earlier lesson. Now I see I have a common term dx dt on my right hand side. So why don't we factor it out? So I'm going to factor out to produce a 15x squared minus 1/2 x to the minus 1/2 power, okay, and then factor out the common expression dx dt, the common factor as an expression dx dt. It's a rate, and then all of that here equals the dy dt on the left hand side. Okay, so this step right here is entirely algebra. Nothing surprising for anyone who is in calculus about factoring a common factor that exists in both terms here. Okay, nothing about that. But now I want you to have a closer look at this current equation right here. It's still an equation. It's still an equation that points out a relationship between dx dt and dy dt. It's still an equation. So in other words, this is just another equation expressing how dx dt and dy dt are related rates. It's just a better version of this compared to this. Okay, but let's have a closer look at this one right here. Let's have a closer look at this one right here. 15x squared minus 1/2 x times, 1/2 times x to the negative 1/2 right here. Let's just have a closer look at that expression. Multiplied with this dx dt right here, where it exists right now inside the parentheses. I'm going to underline that with red ink right there. That expression, ladies and gentlemen, think of our equation from the beginning. Okay, here's how I see the connection right here. Y in the beginning, this problem right here, we started out with y, but so now if we're looking back at the beginning problem right here, it was not only an equation. It was not only an equation. I did not mention this when I introduced the problem, but now let's have a closer look. Let's have a closer observation here. This equation at start was not simply just an equation, not simply just any equation, but it's an equation in a little more special way. This is already an equation that expresses y as a function of x. Let me repeat. This that I brought up in the beginning was not only an equation, was not just, hey, it's an equation involving x and y out there. It was not just simply one equation like any other equations involving x and y out there. It's not just that. It is, but it's not only that, okay? It's more than just an equation. This is an equation that expresses y also as a function of x. Have a closer look. And this is not anything new. This is not anything new. It's just another truth about this equation that I want to point out right here. This equation at start that we're working with is an equation that already expressed one variable generally in terms of the other variable. One variable as a function in terms of the other variable. That's another generality or another general specialty of this particular equation I'm bringing up right there. Okay, so this equation, my point is, it's an equation expressing y as a function of x. Okay, so let's take a good note of that. So this equation expressing y as a function of x. You see, we wanted to treat y as a function of t. Yes, we still want that, but doing this, the only choice for us is treating y as a function of t implicitly. But this is explicit right here. This is explicitly, see, this is explicit. Right? Explicitly, y is already written as a function of x. That's what I want to point out. And generally, this problem starts bringing you into that generality that a lot of times when your equation that you're working with, that you're about to find related rates out of that equation, already express one variable as a function explicitly in terms of the other variables. Okay, we're getting there for that. We're getting ready for that. But so now, just now, back to this problem right here. Well, then, so what? What about it? Now we know, well, all audiences of mine know that this equation here expresses y as a function of x. Well, what's good about that? I mean, why do I have to bring that up? Then in that case, this expression right here, where I underlined in red ink earlier, this is indeed, ladies and gentlemen, this expression is exactly the dy dx right here. That's something to point out. This expression right here, think about it. Your equation from the beginning was y equals 5x cubed minus the square root of x, or you can alternatively write that as an x to the 1/2 power. Use your own understanding to verify me. Find the dy dx of this equation. Find the dy dx of that equation. Treating y as a function of x already, as I pointed out from the other board. And so isn't it true that dy dx here has to be a 15x squared minus 1/2 times x to the negative 1/2. And that's what I just pointed out right here. That's what I just pointed out right here. This, all of a sudden, we realize it turns out that, hey, the this equation, we apply our understanding about the implicit differentiation, and then we came out with an equation that relates the dy dt and the dx dt rates here. And that's why we call these two rates, the dx dt and the dy dt, as related rates. But all of a sudden we realize one further the underlining concepts behind the scene right here. So in this case right here, for this particular equation, we realize, hey, so dy dt, or maybe let me write in a separate space right there. Okay, so now I've had this here long enough. So from what we've done here at this point, I now realize, wait a minute, so dy dt that we're looking for is related with dx dt by simply dy dt equals dx dt multiplied with dy dx. Dy dt is what we were looking for initially, and is now proven to be related to dx dt through this relationship. But hey, wait a minute, look at that dy dx here. Look at that dy dx here. What is a dy dx? This is another rate. This is another rate. Well, the dy dt in our interpretation at this point of your understanding, dy dt is a rate of change treating y as a function and t as a variable, rate of change of, in terms of the t variable. This is rate of change of x in terms of the t variable, but this is rate of change of y in terms of the x variable. They're all rates, rate, and rate. So in the end, this is another rate of change. This is another relationship between rates. We got 3 rates involved. 2 of those rates are in respect to the t variable, and one of those rates is in respect to the x variable. Okay? And that's all for this particular problem. And we are so close to hitting to that main core thing I was about to introduce. All right, so now let's take a pause and let's put that as, let's call it an end to this particular demo problem right here. I'm going to get back to my other boards, erase out the board, and bring up a generality right here. All right, so right from the beginning of this problem, here's a generality that that there was a generality behind the scene here that now it's time to bring it out. Right from the beginning of this problem, that equation y equals 5x cubed minus the square root of x, as a generality, or generally, we're understanding that as the following. A lot of times in your work, and when you're especially when you're working with the problems to come up with related rates, a lot of times you run into the following. You run into a situation where one variable, let's say y, is explicitly expressed as a function of x already. That's what happened to our earlier y equals 5x cubed minus square root x. This is what I purposely want to bring out as a generality. Again, a lot of times throughout your work, throughout your process, working through a lot of application problems out there, working on related rates, then a lot of times you're in that situation where your equation right from the beginning, your equation is already in the form of your equation already expressed a one variable in terms of the other one. One variable being expressed explicitly as a function in terms of the other one. All right. So keep that idea in mind. One variable, okay, is expressed or already expressed as a function. Okay, in terms of the other one, I mean the other variable. So one variable is already, so that's the y right here. I call that some other case. You got p equals some function of v. You got r equals some function of x. One variable is already expressed as a function in terms of the other one. Okay, so that's one big thing to keep in mind about this generality I'm about to give. Then if that's the case, if that was the case for us, surprisingly things are made easy for us here. But still, in the end, we want to do the following. We want to differentiate. Okay, with a function, with an equation like that, we still want to differentiate. So we want to differentiate this equation in terms of some t. So I use t here, but the point is t is a variable that's currently not present in this equation. Just like that same old concept. So again, generality, or as a generality, or in general, a lot of times when we're working with the equation to find related rates, we ran into a case where, or we ran into a situation where in our equation it already expressed one variable as a function in terms of the other one. But out of the two variables here, we want to differentiate our equation in terms of t, and basically in terms of some variable that's not currently present. Nail that down with me for me on that. Okay, and so in that way, I wrote this down earlier. So now I want, when we're doing that, yes, the usual work, according to what we usually understand, we want to see y as a function of t, of course, and further we want to see x as a function of t. But even more importantly, focus on that, because x is already, in this equation, x is already the variable that drives the output of this function. And so once you can see x as a function of t, then needless to say y will also be a function eventually in terms of t. But focus more on this. So we want x as a function of t. We want x as a function of t. I'm so short of board space here, so allow me to write this down. But make sure you write this note down on your paper somewhere if you're learning directly from this lesson right here. It will be beneficial. Okay? I want to see x as a function of t. More specifically, I want to emphasize on that. I want to see x as a function of t. So x is a function of t. And now y is a function. Y is a function of x. From that, like I said, and I wrote things down in a certain order. Let me repeat. I want my students to focus on the fact that x is a function of t implicitly, but y is a function of x. X is a function of t, but now to find y is expressed as a function of x. So all of a sudden we realize, and it doesn't even have to be any particular problem that I gave you anymore. Just look right here, and I will bring out things that you have seen and become fluent already. The function f is the outside function. And then the function t right here, allow me to underline that with red ink. This is the inside. This is the inside function. Okay, to make it consistent with my lecture where I talked about the chain rule. The chain rule. And so now f here is the outside function. All right. And so now just back to what I was arguing earlier. Needless to say, once we understand x as a function of t, and then y is a function of x, then eventually y will eventually be a function of t. And so in that way, now, ladies and gentlemen, okay, to find dy dt, to take the derivative of this overall function in terms of t, see, because I highlighted it earlier, once we have seen and agree with each other, okay, once we have seen and agree to ourselves that the problem wants x as a function of t, and then y is already expressed as a function of x, y is a function of x, then eventually y will also be a function of t. And that's why it is completely possible to find, and it is completely legal to find a dy dt, the derivative of y in terms of t. All right, but hey, let's look at the structure of this current form I'm writing right now. There's an outside and there's an inside. I brought that in for a purpose. According to the chain rule, we know this. From the chain rule, we know this from our learning about the chain rule. So needless to say, this lesson also must be learned after you have learned about the chain rule. Okay, without the chain rule, we cannot move on in calculus. Okay, and so now, according to the chain rule, I need to take the derivative of the outside, which is f prime, but keeping x the same. I believe I've yelled out loud multiple times throughout my lessons, specifically where I gave the understanding, where I gave lecture about the chain rule. We take the derivative of the outside, keeping the inside function the same. But then chain rule stated chain rule has a further statement. We have to multiply that derivative of the outside with the derivative of the inside, which is x prime of t. So this is straight out, this is the raw form, this is the raw format. This is the raw format of the chain rule. Okay, so from that understanding, we lead down to, hey, to find dy dt, this is chain rule. We got to apply chain rule. We're saying that out through the mouth fluently at this point. To find this, the derivative of t, the derivative in terms of t, from this function, we got to use the chain rule. The chain rule says take the derivative of the outer function, of the outside function, and then multiply that with the x prime of t, the derivative of the inside function. All right. So now, allow me to move on to the other space and continue my arguments here. And so now let's look at that chain rule line I had earlier. So of course, by the way of the chain rule, a very important result that was proven by past mathematicians, the chain rule. dy dt from that very last line I wrote on the board allowed me to rewrite that here. We want the derivative of the outer function, keeping x, and now in this way I'm even gonna skip the x of t. I'll just say, hey, find the derivative of the outer function. That is f prime of x. Even though earlier I wrote x of t, but it's making it a little more confusing. So now, to even make it more condensed, f prime of x. And then, since x is a function implicitly defined as a function of t, we have to multiply with the derivative of the inside function. So that's why we multiply with x prime of t here. So that was the exact line I wrote from the other board. And now I'm putting it here, but I purposely skipped out that in parentheses t, because I want to start triggering up your attention here a little bit. I want to start turning your focus into a nicer direction right here. All right, ladies and gentlemen, right here, the x prime of t, what do we understand that as? We understand this as dx dt in Leibniz symbol, in Leibniz notation. And then we multiply that derivative dx dt with, so now ladies and gentlemen, think of this a little more closer in terms of the Leibniz notation. Okay, that's why now earlier I had a lecture to point out about, you know, the some usefulness of having different ways of writing your derivative symbols. And then this prime symbol, and we are outside of that, we have the dy dx symbol and the dy dt symbols. I also show where they originated from. And so at some point, if you can use all of those symbols flexibly and interchangeably, you will reach, you know, a limitless amount of usefulness. You will reach a limitless amount of usefulness that empowers your understanding. So I see this f prime of x right here as a dy dx. So in the way how I see on the right hand side of my equation, dy dx as a rate showing how much y changes per change in x variable, multiplied with the rate of how x changes per change in the t variable. And that product here equals the dy dt on the left hand side. This is the rate of how indicated. This is the rate indicating how y changes per change in the t variable. So I came to this point completely using the chain rule over here. But hey, isn't this what exactly looked like the relationship I pointed out in that demo problem earlier? Y equals, in that demo problem we had y equals 5x cubed minus the square root of x. We went our way, we spent a lot of work, okay, and in the end I pointed out this result right here, dy dt, okay, equals, now in parentheses 15x squared minus 1/2 x to the negative 1/2. There's no need to put that as a square root expression, but multiply with the dx dt. Allow me to write this symbol dx dt in that visible part of the other board. But so I made it further, I argue further when we were still working with that demo problem. So I came up with the dy dt was recognized, was realized to be, this is our dy dx, and multiply with the dx dt. So this that we just now really proven, that we have just now really discovered, already lived in our problem earlier when I was demonstrating that idea. Like that. All right. And so now, this is a fundamental understanding. The idea now is that, see, from this point on, this is how I see it. See, it was a chain rule that led us to here, and then in the end, this is still the chain rule. As a matter of fact, over 90% of the textbooks, anytime the textbook introduces about the chain rule, somewhere here and there, 90% of the textbook will also include this line right here. It's a different way of expressing the chain rule. Believe me, it doesn't matter if you're using a James Stewart's textbook, the very standard and famous textbook in calculus ever. Okay, sadly the author already passed away, but even if you are using the James Stewart textbook and many other textbooks out there for calculus, any standard college level calculus textbook, including the high school level calculus textbook, any calculus textbook, when it comes to writing, when it comes to the teaching about the chain rule, over 90% of those textbooks will have another line. So this is commonly seen, this is definitely seen in all calculus textbooks, but over 90% of textbooks will also include this line as a different interpretation, of the chain rule. But see, when any students arrive in a textbook to that particular section in a textbook where it talks about the chain rule, you probably don't see much usefulness of this line yet until now, when you are being experienced through with some related rates. So now all of a sudden we look back at this relationship right here, we realize, hey, chain rule already pointed out for us since long ago that this chain rule now is understood as related rates. Chain rule is understood as, or points out a relationship between rates. We actually have 3 rates. In this particular situation here, we got a dy dt rate, And then that's related with the dx, the dy dx rate and the dx dt rates. 3 rates are all related. And that's why, I gave this talk about how chain rule can be seen as related rates. Okay, so that's about the introduction of the idea. That's about the introduction of the idea. So just think about the impact. Just think about the impact. Okay, why do I want to bring this up? And why do I feel that it will be beneficial for any one of my students? Think about this. The point of learning calculus is that you will see a lot of problems where you can apply calculus in your work there. You're going for engineering. After viewing this lesson and after learning calculus, you will see that calculus has a huge amount of applications in the engineering field. You're going for physics. Calculus has also a huge amount of application for physics. As a matter of fact, one of the mathematicians believed to be the father of calculus, he was himself also a physicist, Sir Isaac Newton. Okay, so no doubt that a physicist needs to learn a massive amount of calculus because these are all applied in physics field. Okay, you going for a chemistry major? When it gets to immediately in what I remember from my own education, when you learn through the inorganic chemistry, there will be problems where it brings in your understanding of the calculus to find the derivatives. It will come. So you see these applications anywhere. And for students who are going for for students who are going for the business, economy, okay, rate of change exists all over in your applications. So never give me that excuses that professor, I'm going for business field. Why do I have to learn so much calculus? Calculus exists in almost every work of your daily life if you are going for a business career path. Okay, if you're going for the medical field or health science, calculus exists right in any of those applications. For example, if you're injecting a medicine into a body, the way how the medicine gets distributed throughout your entire body, there's an equation that describes that action where the medicine gets dispersed into your body, and then we can take derivative to measure rates, how fast it goes through your body, it gets distributed out throughout your entire body. Okay, calculus lives in anywhere in your applications, and this particular thing about the related rates is particularly useful. And so now let me point out a few things right here. A lot of times for physics people, okay, we measure, for example, spring constants as a force right here. So if force is a variable, spring constant, say, it's always, the Hooke's law, basically, that's what I was saying right here. So the amount of force that you apply on a spring is always minus k, this is called a spring constant, times x, how far you stretch, or so basically this relationship here points out how much force you need to exert on a spring, either to stretch it or to compress it from its natural length right here. But see right here, we have an equation of two variables. K is regarded as a constant, so every spring has its own spring constants. But in the way I see it now, force is a function expressed in terms of the x variable. Okay, so if we have to find the df dt and then the dx dt and all that, then with something like this, df dt, the rate of change of force, how we change force, because everything is changing. That's why we need to measure rate of change. So df dt is equals to, now this is df dx right here, will be for sure equals df dx multiplied with the dx dt. Okay, and I'm not saying that this is all of those applications for the physicist. Okay, this is not all of those applications for the physics students right here. You will explore a lot more as you go through your formal physics course. Okay, but see, just like that generality that came out, because now I see one variable expressed as a function in terms of the other variable. And so now chain rule says if I eventually want df dt, where t is a variable that's not currently present in our function. That means f is a function of t eventually, and x is definitely a function of t. And so altogether, this came straight out from the chain rule. And so this is just another way this is just another version of our relationship right here. It points out the relationship of three rates. There's the rates pointing out how our force exerting on that spring changes over time. Okay, how the distance. So x here is the distance, how far we stretch or how far we compressed from its natural length. So x here is the variable representing length of the spring right there. And you will get all of that complete explanation when you're taking a formal physics course right there. Okay, allow me to only be brief. So x is a variable, so change in x over time, okay, and also, so now we have another rate right here, the amount of change of force per distance that we're changing, per distance that we either stretching or compressing. It's a related rate equation. It brings up one example. It points out one example where you see the usefulness of what I pointed out here for anyone heading out for physics. And of course, the engineering students also have to go through a heavy amount of physics courses as well. I'm quite sure you will sooner or later see this kind of equation as well. Okay, so this is something to share for the audience, for the students who are learning from my lesson here, but planning to head on to a STEM field. Okay, physics, math major, chemistry, science field. You will see this a lot. Okay. For students who are going for business major or the econ major like that, okay, then a lot of time you're looking at revenue. When you're making a business right there, we always want to look for our revenue. We're looking for way to make revenue, and then after revenue, subtracting away cost, you bring in for your own the profits. That's the money that's going into your own the budget like that. Okay, so but it started out with revenue. So revenue is a lot of time expressed as a function of quantity. A lot of times, very commonly, and again, my role here right now is not to explain, is not to be an econ teacher, or my role right now in this lecture is not to be a business professor. So I want you to learn this details from your own business professor or econ professors, but I can guarantee you a lot of time in your own applications, revenue will be expressed as a function of Q, where Q here represents the quantity. See, so we got two variables again. So it falls right into this generality. Revenue is a variable. It's already expressed as a function explicitly in terms of another variable, the quantity. All right, and so in that way, here's how I see it. And there will be times you are asked to find, dr dt. How fast our revenue changing over time. Time is one of the most important the parameter in this life that we're living in right there. Okay, it doesn't matter what field that you're going in. So you want to, for business major students or business people, okay, you want to measure how fast your revenue is changing over time. And right here in this equation, time is not directly present in this equation. This equation only relates R and Q. Revenue relates with quantity. Okay, but time is always behind the scene. That's why it's implicit. Okay, so think about if you in that position when you want to find dr dt, then see, according to this generality we have just learned, as an application now, as a good place for anyone going into business field or econ to apply, think about dr dt here can be found by getting a dr, the derivative of r, but in terms of q, dr dq, and then multiply that with dq dt. Okay, that is how I see another related rate. It's just another version of saying this is just another version of this exact form that I brought up right there, where we see this in business field right there. Okay, for a lot of business students. All right, and so now, of course, I'm not going to end the lecture here yet. Okay, even though all of the main idea is finished here. But now it's time to do a couple examples right in this particular problem right here, right in this particular lecture here, so that you can get a hang of that and get real comfortable and real fluent with utilizing this new understanding. And really, it's not new, but it's just, hopefully I trigger it out, and it will become something that's quite useful for you, because you will commonly see this a lot in your the daily applications out there. Okay. All right, so now right here in this lecture, allow me to introduce example 1. We just want to get comfortable by going through a few repeated problems, where we keep repeating our understanding so that we get comfortable with that. So here's the worded instruction of our example over here. Let's differentiate, okay, let's differentiate in terms of t, okay, to find the related rates. All right, and allow me to underline that term related rate there. So we want to differentiate in terms of t. Differentiate what? So of course, throughout this particular exam 1, I am going to be giving out about 3 or 4 problems. So each problem is an equation itself. So we want to differentiate each given equation in terms of t, okay, to find the related rates. And I underline this term right here because right now at this moment I'm not able to explain why it's plural here, but we will get there, and I will come back and explain why I have this term here as we finish our first problem in this particular example. Okay, so now here comes our first equation. See, in the end, it's an equation. It's an equation. Part A. Okay, our equation is y equals, okay, so y equals natural log of x squared plus 1. Natural log of x squared plus 1. Natural log of x squared plus 1. Okay, so yes, all I need you to see now is it's an equation. It's an equation. There's y variable, there's x variable, 2 variables present, currently present in this equation. That's it. That's all I want anyone learning from this lesson to see. But now the worded instruction of the problem is asking, hey, let's differentiate this equation. Let's take the derivative of this equation, but differentiate in terms of t. And so now we realize that, hey, throughout the entire equation here, the variable t is not currently present at all. So that means y can be a function of t, and x here is also regarded as a function of t. And further, I realized, alongside with what I have explained and spent the most time explaining in this particular lecture, I realized that this is an equation that already expresses y as a function of x. See, it's at this point, for anyone learning in calculus, when you arrive at this level, you should have been familiar with a logarithm already, and particularly how to find the derivative of a logarithm function. Okay, doesn't matter which academic path you're going for. But now, generally speaking, I'm seeing this as a function expressing y as a function of x. And then x, on the other hand, is a function of t. And so eventually y will be a function of t. No doubt about it. Okay? And so now that's why, so now to find, see, now we want to differentiate in terms of t to find the related rates. Okay? So this is what I'm doing. So now we don't have to think too complicated. We can just directly apply, because we already realized that this is an equation already expressing one variable in terms of the other one. So now I can just get straight into, see, differentiate in terms of t. So the left-hand side is asking for dy dt, clearly. And the right-hand side, after I have pointed out that we recognize, okay, we recognize that y is a function of x, where x is a function further of t. Then so on the right-hand side, we're going to go ahead and get straight into the chain rule. The chain rule says we take the derivative of this natural log right here. So and be careful with this chain rule a little bit. The chain rule itself See, it's natural log as the outermost, and then inside of that there's still an x squared function here. Okay, so it's 1 over x squared plus 1 times with 2x. This is the derivative of the outer function, the whole outer function, because I see x is the innermost function. So taking the derivative of the whole natural log of x squared plus 1, or in other words, how about to keep it short, I want, this is right here, this is my dy dx. To put it in similar language that for anyone at this point, this is dy dx. Okay, and if you feel like you need to, pause the video to see why I come up with this 1 over x squared plus 1 times 2x. So this is my work to find dy dx. But now I need to multiply additionally with the derivative of the inside function, which is a dx or dt. But now dx dt, x is defined implicitly as a function of t. So now we have no better choice rather than just leaving that as a dx dt here. All right, as a dx dt here. So all together in the end, this is my end result right here. Okay, so now allow me to erase this note right here. So dy dt is equal to, I have 2x multiplied divided by x squared plus 1. Okay, 2x over x squared plus 1. See, this is my dy dx, but gladly we were able to find it. So why not leaving it? I mean, why not finding it and put it here? And then the dy dx here will multiply with dx dt. All right. So ladies and gentlemen, this is what I'm saying that we have done, we have achieved our goal right here. Our goal is to find the related rates. These are all the related rates, plural. There's the dy dt as one rate, there's a dx dt as one rate, and another one right here. This expression now is also another rate right here, the dy dx here. So this is, see, this is dy dt equals 2x over x squared plus 1. This is understood as the dy dx. And then this is the multiply with the dx dt. So that's how the three rates are related with each other. So once again, upon this realization right here, the general idea behind the scene here was, see, the dy dt must be found by just get your dy dx first, and then multiply that with the dx dt. Okay, this is the derivative of treating y as a function of x. Okay, and then we multiply with the implicit derivatives here. That's the essential idea that I was focusing to. And so the dy dx here led me into this 2x over x squared plus 1 as usual. And then on my left hand side is a dy dt, and on the right hand side of mine is a dx dt. All right, and so after part A, part B will pick up a lot faster. Okay, so really this, for anyone, it doesn't matter what career field you're going for, business major, math major, physics major, whatever, this function is quite common out there. Okay, so I don't need to bring out an application of where you see a function like this. Okay, let's head on. All right, so let's look at part B of our example. So now I'm going to point out another equation. So right at start, everything you have to see here is an equation. So how about V is a 4/3 pi r cubed. V is 4/3 pi r cubed. Okay. So in which application do I see this equation? In which application do I see this equation? Ladies and gentlemen, this equation here is the equation that calculates the volume of any sphere at a given radius. This is a pi, it's a constant, 3.14 and a lot longer. So no need to argue about it. This is a constant. So 3/4 pi is a coefficient. So in the way how, so that's just to point out the application. And I mean, which field deals with the spheres and circles? Physics field, engineering field. A lot of time you're calculating the spheres and volume, and you know, you even build structures that has spherical shape. That's the formula you need to use. Okay. But now in the way how I see it right now, And allow me to save this little space right here to make some notes right here. But so in the way how I see v is a function of the r variable. No doubt about it. V is a function. See, one variable is expressed as a function in terms of the other variable. That's why I wrote it down right here. All right, and so now in this way right here, we want to differentiate this equation in terms of t. That means we're differentiating this relationship in terms of t. And so according to what we have freshly picked up in this particular lecture, then dv dt, according to what we have recognized, what we have discovered, then we can just simply treat this as a dv dr multiplied with the dr dt. We have just now differentiated and with the formula, a quick, fast, convenient formula. So now all of a sudden we also realized that it became a formula for us to use. Anytime we recognize our equation expressed one variable in terms of the other variable, as a function in terms of the other variable. All right, and so now right from this understanding, then that means right into my equation here, dv dt must equal to, okay, so now I'm going to go ahead and find dv dr right from that. So dv dr, well, just the usual power rule is going to kick in. So we're looking at 4/3 pi times 3 r squared. That's dv dr. This is dv dr. All right, and we multiply that with dr dt as the formula was stating, as the formula stated. All right, and so in that case now, let's finalize our final equation that points out the related rates. Okay, so we already recognize 3 rates right here, but this rates, the dv dr is already explicitly written in terms of a function of r right here. Okay, so now all together we're looking at dv dt equals, and so the 3 cancel with that 3, we're looking at 4 pi r squared dr dt. But ladies and gentlemen, this is what we have reached, what we were looking for. We have found the related rates. Now we have found the dv dt is related with dr dt, okay, as through this product right here. And as a matter of fact, again, this 4 pi r squared is another rate. As a matter of fact, it was the dv dr. Okay. So we got 3 rates involved right here in this problem. All right. So now all of a sudden you realize how fast that understanding can help us right here, because it didn't take me as much time compared to part A. Let's now move on to part C right here. So again, I mentioned it earlier. A lot of times students in physics and engineering or even the students who go in for civil engineer, where you're going to be working with a lot of construction, there are a lot of building structures that go in spherical shape. You will need this formula a lot. Okay, so volume of a sphere, maybe it doesn't happen much in your business in a business application, but it happens all over in physics and engineering applications. Okay, so let's head out for another equation. All right, so in this equation part C right here. So how about we have an equation R equals 20p divided by square root of 6p minus 1. All right. So at first sight, just simply see what I gave here as an equation. Okay, just simply see this as an equation. It's 20p divided by a square root expression of 6p minus 1. Okay, so the way how I see it now, R is a function of P. See, this equation has only 2 variables involved. There's the R variable and there's a P variable. Okay, there's the R variable and there's the P variable. And further, I realized that, hey, this equation points out that this equation already expressed R as a function of P. Okay, and then so eventually at that step where we differentiate this equation in terms of t, this is what we're doing. dr dt, according to the chain rule, has to equal dr dp times dp dt. It's straight out from the chain rule, but it now points out a relationship between three different rates right here. All right. And then to give a quick insight of where an equation like this comes from. This is an equation that probably very common to the business field students right here. I mean, think about the R here as the revenue, okay, and the P is the variable that names pricing. So a lot of time, so I talked earlier how, for business, the major students or business field, the professionals out there, then a lot of times revenue is expressed as a function of quantity. And also there are other instances, there are quite many other instances where revenue is expressed as a function of price. Pricing is a factor that can change revenue. Also, quantity can also, on the other hand, be another factor that can also change the amount of your revenue right there. And so that's why, for students who are going in business field or econ, you will see it all over very commonly that revenue is expressed as a function of price. So P here is named after pricing. Okay, or sometimes the revenue can be a function of the quantity, the Q variable or the X variable for quantity. All right. But now, if you're asking me a question, how did they come to that? I have to leave that for your professor in econ or in business to explain something like this, because of course, when you're working with in an actual application, either you hire an analyst to come out with an equation like this for you after he's been observing markets and all that, okay? And then our job here is to take on from what has been analyzed to us and formed into an equation, and we're gonna find rates. That's our job. Okay, so now let's put ourselves in that position that, hey, we already knew that revenue in our case here is expressed as a function of P. R is a function of P in simplest term in math, okay, in simplest math terms. All right, so in that way, we got a formula. We have already got a formula to find dr dt, and then dr dt equals dr dp, because R is a function of P, and then multiply with dp dt. So how do we know? Again, we have done 3 problems. I just want to reinforce. How do I know? It has to be dt here, because we want to differentiate in terms of t. All right, so now we're ready for advancing it and apply our understanding here from our general understanding into this particular problem. Okay, so that means as a formula now, dr dt must equal, now I'm just gonna, all I realize is I will need to find the dr dp here, the derivative of R in terms of P, right from this expression. And that's the advantage for us right here, because we already had R expressed as a function of P. Okay, and so now there are quite a few different ways how you can see, but directly we can use the quotient rule right on this. Okay, and so now I'm looking at, so 20 is the derivative of the numerator, multiply with, now the denominator is inside the square root, so I decide to keep that as a power 1/2. So 20 times 6p minus 1 to the 1/2 power. This is the denominator without derivative. Okay, and I'm going to subtract according to the quotient rule right there. And then now I'm going to have 20p multiply, and now I'm going to take the derivative of the bottom right here in terms of p. So right now I'm just simply finding I should have also emphasized this, but all we do now is just focus big time on that derivative in terms of the clearly the present variable right now. Focus big time on the currently present variable right now to find the derivative, because any other one, it's just a matter of writing it down, but we can't really find it. All right, so now we're going to spend our time finding the derivative in terms of p here. So 20p times, so now I have a 1/2 times 6p minus 1 to the negative 1/2 power, and then multiply with 6. Multiply with 6. All right, because this is the derivative of the inside again. Okay, and just treat the problem as a usual of finding the derivative. And then in the denominator, we divide it by 6p minus 1. Okay, 6p minus 1, this is because 6p minus 1 in the square root, but being square, the quotient rule. All right, and so now I've left this here long enough, so allow me to erase that. because I'm not done yet. All this here is just simply my, all of that here is my dr dp. Okay, all of that big expression right here. And yes, maybe, you know, at this point, having to simplify it or not, it really depends on the teacher. Okay, and then multiply with a dp dt. But as far as finding the related rates, we are done right here. This big expression in terms of p, that's our dr dp expression. And those are the other rates, or they're all related together. Okay, and so allow me to stop the problem here, because, you know, it's just for lecture purpose. I want to emphasize on the understanding rather than spending too much time on the algebraic the simplification. But when you actually do a problem similar to this, make sure you can you find out from your own professor. It could be me or it could be other professors to find out whether to simplify an expression like this. Okay, so here I just want to focus on the concept behind the scene, right there. Okay, and even if it's for my students, I'm not making any guarantee that, you know, I will always leave out simplification. No, there will be times where I ask you to simplify, and there will be other times where I ask you to leave the expression in the way it is. All right, but that's how we have found the related rates. Okay, that's the RDP and multiply with the dp dt right here. Okay, and so now in that way, allow me to bring you into another example. I'm going to navigate over to the other board. All right, so now let's look at example 2 and allow me some time to write down the worded instruction. So how about I'm going to start out by giving an equation. So let P, okay, equals the 1200x minus x squared. Okay, so we have an equation. So let's now find we want to find the dp dt. Okay, if we want to find dp dt if x equals 240, okay, and dx dt, okay, equals 35. We want to find dp dt if x equals 240 and dx dt equals 35. Okay, so let's break down the problem before we head into it, okay, to have a clear understanding. All right, so I'm sure you have seen, like I said, you should only arrive at this lesson after you have already learned from my general, you have learned from my lessons where I gave general understanding about the finding the related rates. Okay, but it never hurts to reinforce the whole idea again. See, from what I see here, this is an equation that only involves p and x. There are only two variables involved. And so it's more, of course, it's a lot more natural that we think about finding dp dx, because it's a rate as well. But here it's the questions right out from the box. The question is looking for dp dt, and then the question has a given information, dx dt. But so these are rates. That's a rate. We want to measure how fast p is changing, okay, over t variable, per the change in the variable t variable. And we want to also, we are given the rate of change of the x variable in respect to the t variable. But critically speaking, the t variable is not anywhere present in this equation. It's just not. Okay, and so that is a good ringing sign right there, indicating for us that this equation here, we have to apply our understanding about the implicit differentiation and further to find the related rates out of that. So definitely we have to see p here somehow as a function of t implicitly, and x here, any one of these two x terms has to be a function of t. And really, I said there are two terms, but really it's just the x variable is just one function. Okay, the same function x of t being involved in two different terms here. All right, and so now That means we want to differentiate. The whole big goal here is we want to differentiate, okay? Even though it's not directly indicated anymore, but what we want here is to differentiate that equation. P equals 1200x minus x squared, right? In terms of t. And like I said, because it was rang up right here for us, okay? These two notations were ringing a bell for us that, hey, we got to differentiate our equation here in terms of t. And again, back to what I pointed out. The t variable is not currently present in our equation, like that. All right, so that's just something to note about. We want to ultimately, even though the wording did not mention this specifically anymore, but we know that our goal is to differentiate this equation in terms of t. I need to clear this out. All right, because I need more space. Now, another thing to realize about this problem. See, our equation here, two variables involved, but gladly one variable p is already expressed as a function in terms of the other variable x, namely x in this equation. Okay, or in other words, allow me to remind you again, right from this equation, I'm seeing that p equals some function of x. And x will eventually be a function of t. That's why we had the dx dt here, and eventually p will be a function of t. But so now, right from that relationship right here, then once again applying what we've just learned in this particular lecture over here, then dp dt as a formula will be dp dx. See, because in the end p is a function of x. So we need to take the derivative, treating p as a function and x as a variable, find the derivative in terms of x first. This is common work for any one of us here at this point. And then we multiply that with dx dt. And multiply that with dx dt. All right. And so now, in that way right here, applying that understanding into our work, here's how I'm seeing it. So yes, dp dt equals, the only challenge for us, the only big work that we have to do, and really the only work we have to do is to find the p dt right out from this equation, which was already given. So 1200x minus x squared is going to give me 1200 minus 2x. This is, ladies and gentlemen, dp dx. And I'm going to multiply that with dx dt. There I have come to my equation pointing out the related rates. We now see in this particular application, we just want to see there are two rates, even though that is also a rate. But we only need to focus on how dp dt is related to dx dt, because dx dt was given, and we want to find dp dt. Okay, and so now once we have arrived at this particular equation that's relating our two rates right here, related rates, these are all related rates. Okay, so once we have come to that equation pointing out the relationship between the rates right here, these given information is now useful. When x equals 240, right at that instance where we reached x equals 240, and at the instance where the dx dt equals 35, we're going to just simply take these values, substitute it right into our current expression. So now dp dt equals, I'm looking at 1200 minus 2 times 240. Okay, I use parentheses anytime I do a substitution. And then I'm going to multiply with, so dx dt is substituted by 35. All right. So that's the calculation setup for that. After this, I am going to swing over to my computer station here and graph a final answer. Okay. All right, so my final answer here, regardless, I mean, disregarding the units, because the problem here right in the beginning did not introduce where we apply this problem to. So let's forget about units right here. But what we are about to have here is the answer for dp dt. Okay, so what I had here was 25,000 and 200. All right, 25,200. All right, and that's how we've done, that's how we see how we can apply our understanding. But specifically, I want to emphasize on the fact that now in this particular lecture, everything breaks down in one short statement. Anytime you're about to do a related rates problem and you already recognize that your equation gladly came expressing one variable in terms of the other variable as a function in terms of the other variable, then we can use the chain rule as a formula that already points out a related rate, a relationship between three different rates right here. And then from there, we just mostly focus our time on finding the main derivative here, the main big derivative. And then that's how it will point out the relationship between the, like here it's a dp dt and a dx dt and all that. All right, and it will speed up the process a lot more significantly. Okay, all right.